Hello and welcome to this presentation on the use of molecular spectroscopic techniques for the analysis of gemstones. My name is Ian Robertson and this presentation is part of the 2020 mining workshop series from Perkin-Elmer. A little bit of a background on testing gemstones, and the question has to be, why do people want to measure gemstones? Of course, gemstones can be an extremely valuable commodity, and it is essential to ensure that a gemstone is the correct type to be able to assign a value to it. Not only do we need to confirm the identity and the origin of the gemstone, but also need to determine the quality of the stone to get a correct valuation. A gemologist will use a variety of tools to determine the gemstone type and quality. A lot of these techniques are manual and requires the great experience and skill of the gemologist to perform the analysis correctly. There are a range of instrumental techniques that can make this task significantly easier, starting with visual inspection under a microscope and refractometry. These are standard tools for the gemologist. However, there are a more technical range of instruments that can provide additional confirmatory information. These include elemental analysis, which will inform the gemologist which chemical elements are present, and molecular spectroscopy, which can be used as a chemical identification technique. In this presentation, I would like to talk about molecular spectroscopic techniques for gemstone analysis. This slide shows the electromagnetic spectrum. We can see that different regions of the electromagnetic spectrum are suitable for different analytical techniques, all giving us different information about how the material is made up. The portion we are concerned about is the region from 50,000 wave numbers to 40 wave numbers, or 200 nanometers to 250,000 nanometers. And these comprise the UV, visible, near-infrared, mid-infrared and far-infrared spectral regions. These regions are significant as they are the regions responsible for interacting with molecular bonds and electronic transitions, which then tell us something about the makeup of the molecule. For these spectral regions of interest, we have a range of instrumentation that allow spectral measurements. The Lambda-365 is a routine UV visible instrument. The Lambda-850 Plus and 1050 Plus are research-grade UV visible instruments, with the 1050 Plus able to measure into the near-infrared region. The Spectrum 3 FTIR instrument is a research-grade FTIR, configurable to measure from the near-infrared through to the far-infrared region. The Spectrum 2 is a routine FTIR for measurements in the mid-IR spectral region. For measurements of very small samples or for impurity measurements, the FTIR instruments can be coupled to an infrared microscope, either the Spotlight 200 or the Spotlight 400. These microscopes can measure areas down to about 5 microns in size. So what types of analysis can we do with the molecular spectroscopic techniques? Firstly, we can identify the gem type, covering situations like, is it a diamond or not? If we are measuring diamonds, then it's possible to classify the diamond type, as we will see later on in the presentation. We can test for counterfeits. We can clearly distinguish between diamonds and any other type of material being passed off as diamond, such as cubic zirconia. It is possible to tell if the gem has been treated. This can be temperature or pressure treatments. It is possible to measure inclusions with this information, leading to a measure of quality. And finally in this list, it may be possible to determine geographical origin of materials. Naturally occurring minerals from different geographical origins will have subtle spectral differences. The measurements of gemstones is not without some difficulties. Normal measurements using the molecular spectroscopic techniques are based on larger samples that are several millimeters in dimensions. Gemstones are often very small samples, and the measurements require optimization of the optics to allow measurements for these smaller samples to be optimized. It can be difficult to visualize and position the gemstone for measurement. The gemstone needs to be in an optimum position for the measurement to be performed. Since the samples are small and can also impact the shape of the sample beam, we need efficient light collection from a range of angles and the ability to focus the beam onto a homogeneous detector. For some diamond measurements, it may require the cooling of the diamond using liquid nitrogen. I will start by detailing the measurements of gemstones using FTIR instrumentation. As I mentioned previously, the IR spectral range covers the near, mid, and far infrared regions. Each of these regions can provide useful information on the gemstone. The PerkinElmer product line consists of the Spectrum 3 and the Spectrum 2. The Spectrum 3 is the research grade instrument capable of measuring across the spectral range from the near infrared region through to the far infrared region using a combination of optical components. The Spectrum 2 is a routine FTIR instrument operating in the mid-IR region of the spectrum. The Spectrum 2 can be easily transported from place to place and can work in the field using battery packs. There are different modes of sampling for FTIR. Samples can be measured either in reflectance or in transmission. In diffuse reflectance, the incident beam on the sample will be reflected back at all angles, and the reflected radiation is detected. If the sample is a clear material, then we will not see a lot of diffusely reflected radiation, but may see radiation that is transmitted partway through the sample until it encounters a sample face and may then be reflected back. In transmission, the detector will see any of the incident radiation that is transmitted directly through the sample. There are a variety of sampling accessories available for both transmission and reflectance measurements on an FTIR that are suitable for gemstone measurements. For transmission, we would use a beam condenser. The beam condenser will reduce the size of the optical beam to match the typical size of gemstones to be measured. A 5x beam condenser will reduce the beam at the sample down to approximately 1.5 millimeters in diameter. For diffuse reflectance measurements, there are a range of accessories from PerkinElmer or third-party accessory manufacturers. For rapid screening of gemstones, we can use the PerkinElmer or the Pike low-cost diffuse reflectance accessories. The real Rolls-Royce of the diffuse reflectance accessories is the Harrick Praying Mantis, and this should be used for detailed gemstone testing. The reasons for using a beam condenser for transmission measurements is explained within this slide. The normal sample beam in an FTIR is several millimeters in diameter at the sample focus point. This would allow stray light to pass around the outside of the sample and reach the detector, thus interfering with the sample measurement. It would be possible to place a small mask in the sample beam to restrict the energy to that passing through the sample only. However, restricting the beam energy is not an efficient mechanism and would greatly reduce the performance of the measurement. Beam condenser optics reduce the size of the beam at the sample focus point to ensure that all the light passes through the sample. The sample is also positioned horizontally, which is considerably easier than trying to mount it vertically. A range of different size masks are available to hold a range of samples of different dimensions. Here we can see a range of spectra of different major gemstone types. We can clearly see that the spectra are different for each type, and this can be used to identify the gemstone. An infrared spectral library can be created for the different gemstone types, and subsequent gemstone spectra can be searched against the library to enable identification. We can also extend the measurements into the near-infrared region of the spectrum, as in some cases the spectral differences are clearer than they are in the mid-infrared region. We can see this clearly for the spectra of emerald and topaz. These spectra were measured in diffuse reflectance. We can use the identification approach to determine if a gemstone is an authentic one or a counterfeit. The most common counterfeits of diamond are cubic zirconia and moissanite. The infrared spectra of these three materials are totally different. Diamond has a distinctive set of absorptions in the 2600 to 1800 wave number range. These bands are absent in the two other materials shown here, and absent in virtually all other mineral types. Diamonds can exist in many different forms, either natural or synthetically grown. The forms are separated into two different types, type 1 or type 2. Each of these types can be further subclassified. Type 1A make up about 95% of all natural diamonds. In type 1A diamonds, the main impurity is nitrogen. In these diamonds, the nitrogens can be in pairs, type 1AA, or in aggregates, type 1AB. In type 1B diamonds, the impurities are diffuse. Type 2 diamonds have virtually no nitrogen impurities. Type 2B having very small amounts of boron as impurities. Here we can see the differences in the IR spectra of two different diamond types. Type 2A has no nitrogen impurities and has a reasonably simple IR spectrum. Type 1AB contains nitrogen impurities as aggregates and has significant absorptions due to their presence. The shape and intensities within these spectral ranges will change depending on the amount of aggregation present. We are also able to differentiate natural and synthetic materials. In this case, we are looking at the spectra of natural and synthetic rubies. The natural rubies show additional spectral bands relating to the mineral structure that's present. The standard FTIR measurements are capable of obtaining spectra from the entire gemstone. However, for gemstone research, it may be useful to look at the gemstones on the microscopic scale. The use of an FTIR microscope allows for measurements on gemstones at the micron level of spatial resolution, thus allowing measurements of smaller features within the gemstone. This will allow for the measurement of inclusions within the gemstone, which could include information on the chemical content of the inclusions. It will also allow for the measurement of contaminations within the gemstone, or determining the distribution of any surface coating or contamination. It is also possible to determine the spatial distribution of clusters or aggregates by mapping the gemstone. PerkinElmer offers a range of UV visible instruments that are suitable for the measurement of gemstones. In the visible region, the instruments are primarily measuring the absorptions due to the color of the gemstone. The Lambda-365 is a routine UV visible instrument that can be used with an integrating sphere for the measurement of diffuse reflectance of gemstones. The Lambda-850+ is a high-performance UV visible spectrophotometer, and the Lambda-1050+ is based on the same instrument platform, but with a spectral range extended into the near-infrared spectral region. Both of these instruments can be equipped with beam condensers and integrating spheres. question is, what can we measure using the UV-Visible-NIR spectral regions, and what information do we get? Similarly to FTIR, there are some challenges associated with performing measurements on gemstones in the UV-visible region. These challenges can be addressed using a 150mm integrating sphere with a beam condenser, or a special design specifically for gemstone analysis that will be described later. The spectral information we get from the UV-Visible-NIR spectral region is similar and often complementary to the information from FTIR. Firstly, we can use the spectra for gemstone identification, thus allowing for detection of counterfeits. It is possible to tell the difference between natural and synthetic gemstones. For some gemstone types, it's also possible to determine the geological origins. Diamonds can be classified according to their type, as described earlier. And it is also easy to determine whether diamonds have been treated, such as high pressure, high temperature treatments that are often used. The challenges are exactly the same as the challenges we faced in FTIR, mainly related to the small size of the sample compared to the optical beam size of the UV-Visible-NIR instrument. These instruments adopt a similar approach in using a beam condenser optic to reduce the beam size to match the small size of the gemstone. There are different methods for measuring the gemstones in the instrument. We can use a simple aperture in the beam that masks around the sample. However, if we do this, then we are throwing away large amounts of energy, and the amount of energy reaching the detector will be very small, resulting in poor quality spectra. The gemstones may also act as an optical component and cause beam shifts and homogeneity errors. It is possible to use a standard integrating sphere to have efficient collection optics after the sample, but these should be used with beam condensers prior to the sample to ensure that as much of the optical beam is passing through the sample. This design works well in most cases, but there are some limitations, especially if the sample has to be cooled for particular measurements. A novel design is proposed to overcome the limitations of such a system. Here is an image of the integrating sphere preceded by the beam condenser. The sample is placed on the integrating sphere. The beam condenser is adjustable, allowing for different beam sizes for different sizes of gemstones. The high energy throughput using the beam condenser generates good quality, low noise spectra. Small gemstones present a challenge for accurate transmission measurement. In addition to the small size, say 1mm to 2mm, gemstones have multifaceted surfaces and a high refractive index. A number of natural white diamonds, a natural yellow diamond, and a synthetic blue sapphire were obtained. Mealy stones. These samples can be fitted into masks with appropriate aperture sizes for the small gemstones. Spectra of very small diamonds between 1 and 1.5mm in diameter, collected with a small beam aperture mask and integrating sphere accessory, and note that the data files were normalized at 800 nanometers. Here we can see the differences between two of the very small diamonds, one being a natural white diamond, the other being a natural yellow diamond. We can see from the plot on the right that the spectra of sapphires have completely different spectral profile to those of the diamonds. An enhanced offering for the measurement of gemstones is described here. The instrument range covers the UV through to the near-infrared region and is a major accessory that fits into the Lambda 1050 Plus detector bay. It's based on an integrating sphere approach. Sample positioning is viewed using a miniature camera, allowing accurate positioning within the accessory, removing the problems that occur on standard instruments and accessories. Cryogenic cooling and electrical heating can be applied for gemstone temperature studies. The accessory is measuring the sum of the transmittance and reflectance, given an absorption spectrum. Here is the schematic for the sample compartment. The sample is placed on a sliding sample holder outside of the sphere and is then inserted into the sphere. The camera module allows the gemstone to be observed and positioned accurately in the beam. Here we see the accessory from above. Here are some spectra obtained from a variety of different samples with different properties. We can see significant differences between the spectra of the different samples, with absorptions in different places throughout the spectrum. So, here we have a summary of the presentation. Both FTIR and UV-Vis-NIR are extremely useful instruments for the measurement of gemstones. The FTIR can be used with both transmission and diffuse reflectance sampling and has the added benefit of being able to look at the samples on a microscopic scale using an FTIR microscope or imaging system. The UV-Vis-NIR measures directly in transmission with the use of beam condensers and integrating spheres and has a special system available for optimum testing of diamonds. The sampling approaches between the two techniques have great similarities, and the types of information that can be achieved are both confirmatory as well as complementary. Thank you for watching this presentation. My name is Ian Robertson and I am a Senior Application Scientist working for PerkinElmer at Seagreen in the UK.